Swayam Prabha. Digital India. Educated India.
So, we were talking about the harmonic oscillator. Let me just remind you of the things that we did. For the harmonic oscillator, potential energy is given by half kx square. The shape of the potential energy curve would be something like that. And the Schrodinger equation itself would be this. And we want to solve this equation subject to the condition that as x tends to either plus infinity or minus infinity, the wave function should approach 0. And the first thing that we did was we made a change of variable. We said that C is equal to alpha times x. We determined the value of alpha. Well, I will write it from my memory, but I hope you can verify this. This is correct, right? Alpha is equal to so much. And then what will happen? This differential equation becomes another one which may be written as d square psi by dx c square plus lambda minus c square into psi is equal to 0, where lambda was defined to be 2e divided by h nu, where nu is the classical frequency of vibration of the harmonic oscillator, right. And then we argued that this equation has asymptotic solutions which are of the form psi is equal to some constant into e to the power of minus c square by 2. It had also another asymptotic solution in which instead of the negative sign you would have had a plus sign, but that we did not want because that will go to infinity as c tends to infinity and it is not acceptable. But this is only an asymptotic solution, which means that this is valid only in the region where c is very large. It is not valid for small values of c, but we wanted a full solution which is valid everywhere, and therefore what we did was we said let us, I mean this is an asymptotic solution. So what we do is we just modify this equation and we say that okay, let us write the solution as h of c e to the power of minus c square by 2. This is the way we will write this the solution, and then our problem is to determine the function h of c, and for that what we did was we took this functional form, substituted that back into this equation, and we arrived at an equation for h, and that equation is d square h by dx c square minus 2c dh by dx plus lambda minus 1, correct me again, I mean if I make a mistake, This is the equation. Please check this. And now the problem is I should solve this equation, and the question is how will I solve this equation. It is not only enough to solve the equation, but I have to ensure that the boundary conditions are satisfied. That means this function psi is equal to so much should approach 0 as c approaches either plus infinity or minus infinity. So, how will I solve this equation? The answer is that the way this equation can be solved is to just assume that h may be written. Let me write it like this. I am going to assume that h may be written as some a0 plus a1 c plus a2 c square plus etcetera up to infinity, where a0, a1, a2, a3 these are constants. Okay, I just assume a solution which is a series, and what I will do is I will try to adjust the values of the constants a0, a1, a2, a3 etcetera in such a fashion that h is going to satisfy this equation. But then if it goes to an infinite series, perhaps I may run into a problem, that if the series is infinite, why may I run into a problem? The answer is that the boundary condition, where is the boundary condition? This is the condition. I have to ensure, I mean even if it is an infinite series, I have to ensure that this series is such that this condition is satisfied. Then only I will have an acceptable solution. Okay. So, what is going to happen is that you see here I will have a term like a j c to the power of j, and then of course it goes to infinity. That is the way the series is. So, what I am going to do is I am going to substitute this here, correct, and see what the result is. So, in order to substitute that, I should first evaluate dh by dc. What will it be? I mean you have the series, it is fairly easy to differentiate it. Derivative of the first term will be 0, the second term will give me a1, next term will give me 2a2 c plus 3a3 c square plus etcetera. In general, what will be the general term? You will have c to the power of j multiplied by what will be the coefficient? A j plus 1 or maybe I will write it in this fashion. If you differentiate this term, what will be the answer? You are going to get j times aj c to the power of j minus 1 plus etcetera. Okay. Because the derivative of this term, what is it? It is going to be j times aj times c to the power of j minus 1. So, let us now calculate the second derivative. Well, when you calculate the second derivative, this term actually goes. So, therefore, you are going to have the first term as that one, you are going to get 2a2 plus 3 into 2a3 c plus what will be the next term? It is going to be 4 into 3 a4 c square plus etcetera. Okay, this is how the series is, but I want to write down the term that contains, let me say, c to the power of j, unlike what I did here. I want to write down c to the power of j term. What will that term be? You can guess what that term is going to be by just looking at this expression. If you have c to the power of 2, then you have a 4 multiplied by 4 into 3. So, therefore, if I had c to the power of j, what I will have is a j plus 2 multiplied by j plus 2 into j plus 1. So, this will be the general term, correct. And now, I also need, I mean, if I look at the differential equation, I have d square h by dx square, but I also need minus 2 c times dh by dx. So, that means I shall multiply this by minus 2 c. So, minus 2 c times dh upon dx would be equal to, what would be the expression? Well, you will have minus 2, I am not going to take the minus 2 inside. So, I will put a bracket, but the c, see, this is my expression for dh by dx. So, I have to multiply this expression by minus 2 c, that is what I will do, but minus 2 I am not going to multiply it, I mean I am going to give it as a common, leave it as a common factor, but c I am going to take inside. So, the first term that I will get will be a1 c, next term will be 2a2 c square, 3a3 c cube plus etc., and this term will actually give me j aj c to the power of j plus etc., and I have to close the bracket. Right, and then the last term in the differential equation is lambda minus 1 h. So, I will just write lambda minus 1 into h, which will be equal to lambda minus 1, which I will leave outside a bracket, and then simply write h. What is h? a0 plus a1 c plus a2 c square plus etc. until aj c to the power of j plus etc. goes to infinity. And now I can just add these things, right, because I want to say that the sum of these three things is equal to 0. So, let me just add up everything, and then what will I do? I will put the result equal to 0, right. Why do I do this? Answer is very simple. I just want to determine the constants a0, a1, a2, a3, etc., right. That is the reason why I do this. So, I want to find a0, a1, a2, a3, etc. So, just add this up. So, for example, if when I am adding, you see, I will be a little bit careful. Here I have 2a2, this term is independent of c. Here there is no term that is independent of c, but there you have a term that is independent of c. So, you just add it up, you are going to get 2a0 plus lambda minus 1 into a0 as the first term, correct. Similarly, you are going to get a term which will involve a1. What will that term be? No, this is not there, sorry, I can now remove this, otherwise I may take something from there. I think I have made a mistake, right. 2a2, I have written 2a0, and I have put the bracket in the wrong place. So, this is actually, please watch out, you see I do make mistakes. So, that is what it is actually 2a2, I have taken 2a2 from here and lambda minus 1 into a0. So, therefore, that is fine. Then the term that depends upon, sorry, not a1, but the term that depends upon C, what is that term? Linear in C. Well, here you will see that it is 3 into 2 a3, into 2 a3, and here it is actually minus 2 a1. And from there what will happen, you will get plus lambda minus 1 into a1, correct. Again I suppose I have not made any mistakes, but then you see I mean I can go on doing this, but what is of great interest is the general term where I have c to the power of j. So, what will that term be? Let me just write that term and be done with this, because that is the general term and that is the most useful. So, what is the coefficient of c to the power of j? Well, you are going to get j plus 2 into j plus 1 into aj plus 2. That is coming from here, that is the term involving c to the power of j. Then there is a term coming from here j aj, but that has a minus 2 associated with it. So, therefore, minus 2 into j aj. And what is the contribution from this line? That is going to be plus lambda minus 1 into aj, correct. So, you have an infinite series, right, infinite series involving C. So, actually if you think about this, this is of the form some constant a0 plus c, sorry, some constant a0 plus a1 into c plus a2 into c square plus etcetera. That is the form of this equation speaking in general, right, and this has to be identically equal to 0. It has to be 0 for all values of c, right. Whatever value of c you put in here, whatever value of c you put in there, this has to be equal to 0, correct. So, how can that be satisfied? The only possibility is that each coefficient in here, when I say each coefficient, the coefficient is a0 or a1, coefficient of c to the power of j has to be equal to 0. That is the way in which this can be satisfied. I mean, it is not difficult to prove this. If you want to prove it, what you do is first you put c equal to 0 into this equation, because this equation is valid for all values of c. So, if you put c is equal to 0, you will find that a0 is equal to 0, fine. Then you differentiate this with respect to c, because this is valid for all values of c, I can differentiate it. If you differentiate, this term will go, the first term will be a1, the next term will be 2a2c plus etcetera, and you put c equal to 0, right, and the right hand side has to be 0, because right hand side is 0, you are differentiating 0. So, the answer has to be 0. So, therefore, if you differentiated this and put the derivative equal to 0, you will find that a1 has to be 0. Then you differentiate it once more and put c is equal to 0, you will find that a2 has to be equal to 0, then a3 has to be equal to 0, and so on. That is another way of arguing the same thing. So, if you had such an equation where you have a power series and the power series is identically equal to 0 for all values of the variable, then the only way that can happen is that each coefficient, right, in the coefficient of c to the power of j in general has to be equal to 0. So, that means a0, a1, a2, a3, a4 they are all equal to 0. So, therefore, if that is the way it is, you can say that well, if this equation is to be satisfied, this equation that we have here, if it is to be satisfied, then this must be equal to, this is the coefficient of c to the power of 0. So, this has to be equal to 0. Not only that, this also has to be equal to 0, right. For each power of c, the coefficient has to be equal to 0, right. So, how many equations do you get? You get infinite number of equations, which you need because you have infinite number of unknowns. You have a0, a1, a2, a3, a4, etc. They are all unknowns, right. So, you want to determine them, and this is the way in which you can determine them. So, therefore, in general what happens is that this term, which is the coefficient of c to the power of j, must be 0. So, this is the only term that I actually need, this is the only condition that I need. Let me write that condition. It says that that is what it says, and this has to be valid for all values of j equal to 0, 1, 2, 3, etc. Now, we can rearrange this. We can say that this means j plus 2 into j plus 1, a j plus 2 must be equal to, I will take these terms to the other side, but you can see that there is a aj that is common. So, I will take the aj outside, and what I will have left is 2 j plus 1 minus lambda. Right, this is what I would have. This actually means a j plus 2 must be equal to 2 j plus 1 minus lambda into a j divided by j plus 2 into j plus 1. This is the condition. So, for any j, this condition has to be satisfied. Now, look at this condition, it is quite interesting, because suppose I put j equal to 0, what will I get? Let me just illustrate what happens. If I put j is equal to 0, what I am going to get is 2j will be 0. So, 1 minus lambda divided by 2 into 1 should be equal to a2. That is what this says, correct. And similarly, if I put j is equal to 1, you will find a1 here. I am not going to write this, you can easily write what it is, and that actually will give you the value of a3. So, you notice that the value of a0 determines a2 and the value of a1 determines a3, but then if I know the value of a2, I can put that value here, right. You put j is equal to 2, then I would have determined the value of a4. So, therefore, from here I can determine a4, right, and from a4 I can determine A6 from which I can determine A8. So, once you tell me what the value of A0 is, right, once you have a value for A0, then that will uniquely determine A2, A4, A6, etc. And similarly, if you had a unique value, if you had some value for A1, that you can put into the equation, you will get A3, then from that you can calculate A5, A7, etc. right. So, this relationship actually determines, I mean this is the general relationship, it determines Aj plus 2 in terms of Aj, and it is referred to as a recursion relation. So, therefore, what we can do is we can have some value for A0 and some value for A1, that we can choose as we like, but then A2, A4, A6, etc. has to be chosen according to the recursion relation, right. So, you choose any value for A0, you will get the corresponding values of A2, A4, etc. and similarly, you choose any value for A1, you will get the corresponding values for A3, A5, etc. and therefore, how many variables do I have which are free to choose, which I am free to choose? I can choose any value for A0, I can choose any value for A1. So, therefore, I have two things that can be independently chosen. Not surprising, why? Because this is a second order differential equation, any solution would have two constants to be determined, and here the way it has happened, the two constants are actually A0 and A1, that is what that is happening, nothing strange. But then I can use an information which is already known to us. The information is that this is a potential that is symmetric. This is a potential that is symmetric. So, that means your solution of the Schrodinger equation, it has to be either symmetric or antisymmetric under the operation of replacing x with minus x. So, if you change the sign of x, the wave function either has to change sign or it has to remain unchanged. So, suppose I am looking at solutions which are symmetric, then what will happen? Well, you have a power series, the power series is of this form, correct, and that power series multiplied by e to the power of minus c square by 2 is the solution. So, when you replace x with minus x, what will happen to c? C will get replaced with minus c, but this term is not going to change, right. This is always symmetric with respect to this interchange, with respect to this replacement of x by minus x or c by minus c. So, what will happen is that this h may be symmetric or it may be antisymmetric, and when is it that h is symmetric? If h is to be symmetric, then what should happen is that I should have only the even terms in the series. I should have A0, then A2 c square, I can have A4 and so on, then the function will be symmetric, and if it is to be antisymmetric or an odd function, then I should not have any even terms in the series, I should have only the odd terms. So, therefore, what I realize is that in my power series I would have only the even terms or only the odd terms, right. So, that means I have two possibilities now. What are the two possibilities? I can put A0 non-zero and A1 equal to 0, right. If I put A0 non-zero, then what will happen? A2, A4, etc. will all be non-zero, and I will get the even solution. or I have the possibility of putting A0 equal to 0, then A1 is non-zero, and what will happen? I will get the odd series, and that means I will get the antisymmetric functions, correct. So, let us say that I will think of the situation where A0 is non-zero, but A1 is equal to 0. Why? I mean, this will give me the solution that is symmetric. Let me mention again what I mean by symmetric. If you replaced C with minus C, the solution will not change, it will remain unchanged, and therefore, it will contain only even powers of C. So, those even powers of C which are in the solution are actually governed by this recursion relation, correct. So, you look at the recursion relation, what does it tell you? You give me the value of A0, then I will calculate A2, A4, A6, A8, etc. according to this recursion relation. And what happens is that the series actually goes to infinity, because you cannot see that anything is 0 anywhere, right? Because you give me a value, I will put it there, I will just calculate. So, then the question is, if it is an infinite series, what is the behavior of that series? Is it a series which will guarantee that this object will tend to 0 when the value of C tends to infinity, right? It is not enough to have any series, the series should be such that that series into e to the power of minus C square by 2 should tend to 0 when C tends to infinity. So, this is something that I want to analyze, and how am I going to analyze that? Well, the answer is this. Suppose the value of C is very large. Well, what we are saying is that I have an H which may be written as A0 plus A2 C square plus A4 C 4. Notice that I am writing only the symmetric case plus etc. This is the behavior, and I am going to analyze the behavior of the series when C is very large. When C is very large, which are the terms that you would expect are the most important? Definitely the terms with large values of large powers of C. That means, I am interested in the situation where the value of J is very large, right, because those are the ones that are important for large values of C. So, if J is very large, what will happen to this recursion relation? If J is very large, you see, it should be possible for me to neglect this lambda or 1. Let us say J is 1000, for example, correct. Then you can neglect the value of this lambda, you can neglect 1 in comparison with 2J, right. So, what will happen? You will have 2J in the numerator divided by J plus 2, you can neglect the 2, J plus 1, you can neglect the 1. So, therefore, J square into AJ. This is the form of the recursion relation when J is very large, right. And therefore, what happens is that this recursion relation becomes 2 divided by J into AJ. So, for large values of J, this recursion relationship actually becomes simple. It simply says that AJ plus 2 must be equal to 2 divided by J into AJ. Now, what I am going to say is that if a series obeys that kind of recursion relationship, then the series actually behaves like the function actually will behave like e to the power of plus C square. That is the claim, that is what I am going to claim. If I have an infinite series where for large values of, let me repeat, I have an infinite series where for large values of C, the recursion relationship is given by Aj plus 2 equal to 2 by j Aj. Then my claim is that the series for large values of C will behave like e to the power of plus C square. Now, if it behaved like e to the power of plus C square, is it acceptable? Well, you look at H, see H is here. I am now saying that if I had an infinite series, this is going to behave like e to the power of plus C square, and e to the power of plus C square into e to the power of minus C square by 2. The net result is going to be, see, one of them is e to the power of plus C square and the other one is only minus C square by 2. So, therefore, the net answer will be e to the power of plus C square by 2, and if it behaved like that, it is not an acceptable solution, because you see this function, this part is decreasing, but the increase in this is huge and is not able to compensate for the decrease caused by the other term. And therefore, what happens is that this infinite series, if I had an infinite series, then I will not get an acceptable solution, correct. This is the problem. So, the question is, how will I get an acceptable solution? Answer is that I should not have an infinite series. The series has to terminate, it has to be a polynomial. The function that I am getting must be a polynomial. I have to manage things in such a fashion that the function h is a polynomial. Okay. Well, before I go into that, how does one prove that if a series obeyed this recursion relationship, it behaves like e to the power of C square? Well, very briefly let me tell you how it can be done. I do not think I need these equations anymore, so let me remove them. So, you see, if you had e to the power of C square, you know the power series expansion for e to the power of x. E to the power of x can be written as a power series. So, similarly, e to the power of C square can also be written. So, what will happen is you will get 1 plus C square by 1 factorial plus C square the whole square by 2 factorial plus etc. Right. This is what is going to happen, which may be written as 1 plus C square by 1 factorial plus C to the power of 4 by 2 factorial plus C to the power of 6 by 3 factorial plus etc. C to the power of nu divided by how much? Or maybe C to the power of j divided by how much? Right, j has to be even the way it is. So, it will be j by 2 factorial, right, plus etc. Agreed? The coefficient of C to the power of j has to be 1 by j by 2 factorial. So, therefore, this series, you see the coefficient of the of C to the power of j, for this series the coefficient of C to the power of j I will denote by bj. For notation purpose, I just call it bj. So, what is bj? It is going to be 1 by j by 2 factorial, right. The coefficient of c to the power of j for this series is actually bj, and it is equal to 1 by j by 2 factorial. So, what will be bj plus 2? Right. The next term is going to be bj plus 2, and what will that be? It will be equal to 1 by j plus 2 by 2 factorial. Agreed? And that will be equal to 1 by j by 2 plus 1 factorial. Correct? I mean, why do I do this? Because I want to find a recursion relationship that is valid for this series and to show that that recursion relationship and this recursion relationship are the same. And because the recursion relationships are the same, the behavior of this series and the behavior of that series has to be the same. That is the reason why I am doing this. So, therefore, now let me calculate bj plus 2 divided by bj. How much would it be? Well, the answer is, unfortunately I ran out of space there, difficult for me to write. bj plus 2 divided by bj will be equal to j by 2 factorial in the numerator divided by j by 2 plus 1 factorial in the numerator. That is all. And this, I mean, this is very easy to simplify. It is of the form is it some number n factorial divided by n plus 1 factorial. That is all, right. This is of the form some number n factorial divided by n plus 1 factorial, well, the answer is 1 by n plus 1. So, therefore, what will happen is that this will just become 1 by j by 2 plus 1. That is all, very, very simple. And therefore, what happens? I find the recursion relationship for this series. It simply says that bj plus 2 must be equal to bj divided by j by 2 plus 1. That is the recursion relation for this series. And if the value of j is very large, what will happen to this recursion relationship? If the value of j is very large, you can neglect that 1. And then what will you find? You will find that bj plus 2 must be equal to 2 divided by j bj. And therefore, I have actually proved what I wanted to prove, namely this recursion and that recursion are the same, and therefore, the behavior of this series is just the same as the behavior of that series, and therefore, this series will behave like e to the power of c square for large values of c, and hence is not an acceptable solution. Well, you see, I seem to be arguing against myself. I found the solution and then I am arguing that this is not a valid solution. Well, it is not a valid solution if it has infinite number of terms. So, what is the way out? It should not have infinite number of terms. I should be able to terminate the series at some power of c. How will I do that? Well, there is a very easy way out. See, you look at the lambda. What is lambda? lambda is given here, lambda is given here. So, if you give me some arbitrary value of energy, so the value of lambda is something, and the series will actually go on to infinity and you will not get an acceptable solution. But suppose it so happens that lambda is equal to let us say 11, suppose, just to illustrate, suppose lambda is actually a number like 11. So, if lambda is equal to 11, what will happen? Suppose if lambda is equal to 11 and suppose I put j is equal to 5, suppose I put j is equal to 5, on the right hand side I will have A5, on the left hand side I would have A7, but then I will have 2 into 5 plus 1 minus lambda divided by 7 into 6, right. This is the okay. I was actually saying that I am concerned with the even series, and now suddenly I switched over to the odd series. It is better that I say lambda is equal to 9, suppose. Then what will happen is that I will have 2 into 4 here, and I am thinking of A4, and 5 into 6 into 5, and this will be A6. I mean, just to be consistent with what I was saying earlier, I was saying okay, I am only concerned about the even series, not about the odd. So, imagine that I have a value of lambda which is 9, and imagine that I calculate A6 from A4. Then what will happen is that you will have 2 into 4 plus 1 minus lambda divided by 6 into 5, and if I say lambda is equal to 9, you can see what is going to happen. A4 is not 0, but A6 is 0, and if A6 is 0, what about A8? A8 is determined in terms of A6. So, if I have lambda equal to 9, then what will happen is that I will have A0, A2, A4, and starting from A6 all the terms are 0, and therefore, I have successfully terminated the series at a finite power of C, and I will have an acceptable solution. There is absolutely no problem, because this H is a polynomial, and any polynomial multiplied by e to the power of minus c square by 2 will tend to 0 as c tends to infinity, and therefore, everything is fine. So, therefore, what is the solution? The solution is very simple. I should have lambda equal to what? If I had lambda is equal to 2n plus 1, where n is an integer, right, then what will happen is that a n can be non-zero, but a n plus 2 will be 0, and if a n plus 2 is 0, everything higher will also be 0. So, therefore, in order to get acceptable solutions, I should have lambda is equal to 2n plus 1. If I have lambda equal to 2n plus 1, guaranteed I can have acceptable solutions, right. And what are the values that I can have for n? N may be 0 perhaps, it may be 2, it may be 4, it may be 6, and so on, right. Why these even numbers? Because I am only thinking of the even solution. If I had thought of the odd solution, exactly the same thing is going to happen, and then n can have the values 1, 3, 5, etc. So, therefore, the final result is that n can have the values 0, 1, 2, 3, etc. And further lambda should be equal to 2n plus 1. If that is the way it is, I will get an acceptable solution. And what does it mean in terms of energy? Lambda is related to the energy by this relationship. So, 2E divided by h nu must be equal to 2n plus 1, or that means E must be equal to 2n plus 1 divided by 2 h nu, or that means E must be equal to n plus half h nu. E must be equal to n plus half h nu, then only you will have acceptable solutions, otherwise you are not going to get acceptable solutions. Fine. And further, this lambda is equal to 2n plus 1 can be put here, right, and therefore, what we are actually looking for, the solutions that we are looking for have, instead of lambda minus 1, you would have the number 2n here, where n is an integer, right. Okay, we will stop here. Thank you for listening.